In this video, we'll be introducing our study of motion by talking about what motion is and the difference between distance and displacement. Move, movement, motion. These are words that we use all of the time in our day-to-day life. If we sit down and actually think about the definition of motion, what comes to mind? Let's look at some examples to get ourselves thinking about what motion really is. Here we see an example of some high-speed motion, this car careening down this road off into the guardrail. Another example of a ball in motion. Definitely the head of the person that's being hit by the ball is also in motion, as well as the arm of the person throwing it. Here we see the orbit of Earth, or the rotation of Earth along its axis. Definitely another example of motion. Here we see this alien figure hitting these sick moves. He's not going very far, but he certainly seems to be moving in some way. Another example of motion is this snail. He's moving very slowly, but he certainly is still undergoing some form of motion. And finally, another very applicable example of motion is our very own Perseverance 2020 landing on the surface of Mars. Pause the video for a moment and try to come up with your own definition of the word motion within the context of physics. So when we say motion in physics, we are defining it as any change in an object's position or orientation. So when we say position, we can mean moving from one place or one point to another. When we say orientation, we can talk about the positioning or the way an object is facing. So simply rotating or spinning or turning an object around. So now we'll talk about a couple of words that will be very important in our understanding and our study of motion and how objects move. The first is distance. Another word that we actually use a lot in our everyday vocabulary. The distance between things. How much distance did that go? So when we say distance, do the same thing. Pause the video for a moment and try to come up with your own definition. So in physics, we use distance to describe the amount of space between two objects or 2 points. This also is used to describe how much ground or how much space an object has actually moved or traveled. The units for distance are the meter, which is abbreviated lowercase m, or the kilometer, which is abbreviated lowercase km. The kilometer is actually equal to 1,000 meters. Let's look at a couple examples of how distance could be used in physics. So here we see a very basic example, 2 points on this grid, and we can see that the dotted line represents the distance or the amount of space in between those 2 points. We could also imagine, if this were a map or some sort of representation, that if an object were to move from one of these points to the other, that dotted line would also represent the amount of space that that object had moved or traveled. Another example here is this diagram of the path of travel of this bicyclist. So we can see, starting down at the tree at point A, we can see that from point A to point B, from the tree to his home, he has traveled 4 meters of distance. We then see that from his house to the tree at point C, he's traveled another 3 meters. That means that the total amount of distance that he has moved would be equal to 7 meters. We can see between the tree at point A and C, the distance between those 2 points is represented by that black line, and we see that that is equal to 5 meters. Another example of distance is the space between our planet Earth and Mars, the planet that we are trying to land on. Now this is a distance that is constantly changing based on the orbit of Mars. But at the closest distance that these 2 planets can be from each other, they are 55 million kilometers apart. That's pretty far. That's a pretty long distance. At their furthest distance, Earth and Mars are 400 million kilometers apart, and even further distance. And that gives you a little bit of an idea of how much space Perseverance needs to cover in order to go from Earth to the surface of Mars. Now that we've talked about distance, we'll talk about another term used to describe motion, which is displacements. When we say displacement, we are describing the space between an object's initial position and its final position over the course of its motion. When we talk about the displacement, we are talking about the shortest straight path or straight line between these 2 points. The units for displacement are also the meter and the kilometer. Let's look at some examples to make this make sense. So in our first example, we looked at the path of this bicyclist going from the tree at point A to his house and then to the tree at point C. We talked about how those red arrows represent the distance of his path, or how much space he actually covered in his motion, which was equal to 7 meters. However, if we were to think about this bicyclist traveling along this path from point A to point C, though his distance is 7 meters, his displacement, or the space between his initial position and final position, is actually represented by that black line, which is the shortest straight path from point A to point C, meaning that his displacement is 5 meters, even though he covered a distance of 7. Here's another similar example. If we were to think about these lines as 2 different points in space and an object were to travel along that curved black line from point A to point B, he would cover the entire length of that curved line as distance. However, his displacement, or the shortest straight path from his initial position to his final position, would actually be that shorter blue line, which would represent his displacement. Now here's a little bit more interesting of an example. If we look back to that very first example where we see the distance between point A and point B, take a moment to think about what the displacement would be of an object that might move from point A to point B in this example. Pause the video and think about it for a moment. So hopefully you were able to put together that the displacement of an object that traveled from point A to point B in this example would be exactly equal to the distance. That is because this path of travel is already the shortest straight path from that initial position to the final position, making the displacement exactly equal to the distance. Now let's look at a quick example of finding distance and displacement of a moving object. So in this example, it tells us that Joey drives his Skidoo 7 kilometers north. He stops for lunch and then drives 5 kilometers east. What distance did he cover and what was his displacement? So if we look down here, we see that in our grid, each one of those squares represents 1 kilometer. We're also told that the green dot here represents his starting position. Now in our example, it tells us that Joey drives 7 kilometers north. So using our compass as a guide, we know that straight upward represents north. And this question is telling us that Joey traveled 7 kilometers. So that would be 7 grids to the north. We're then told that he stops for lunch and then continues driving 5 kilometers east. So again, using my compass as a guide, I can see that Joey then traveled 5 kilometers over to the east. Now I'm ready to think about the distance that he covered because that was his full path of motion. So I can see that Joey's distance was first this 7 kilometers north and then 5 kilometers east. So in order to determine his full distance traveled, I would simply add his paths of travel. 5 kilometers and 7 kilometers means he covered a total distance of 12 kilometers. Now his displacement will involve a little bit more math because we know that the displacement of his travel is equal to the shortest straight path from his starting position to his final position. We know that that is simply a straight line between the points, which would look like this. Now you'll remember from math class, in order to find that length or that side of a triangle, which is called the hypotenuse, I would use the Pythagorean theorem to find out that distance. So I would say that a squared plus b squared is equal to c squared. I would want to solve for c by taking the square root of a squared plus b squared, which if you do all of that math gives you 8.6 kilometers, telling me that though Joey traveled a full distance or covered 12 kilometers of distance, his displacement, or the distance between his initial and final position, is only 8.6 kilometers.